when you check your handout, there were some details about the decision tree diagrams. So let us go through the decision tree diagrams to see what we can get from the details. We can now go to the decision tree diagrams. When it comes to the decision tree diagrams, it is like number 2 in the handout I'd given you. It is number 2 in the handout that I'd given you. So when it comes to the decision tree diagram, they say that it is the diagram that will represent the decision-making process, especially for the routine decision. So the major aim is to identify alternative decisions using the decision node. So we are told that the major aim is to identify, number being is different states of nature which influence the possible outcome as indicated by the outcome node. Then C will be the conditional payoff of each possible alternative decision outcome. So under the capital budgeting decision tree involves the use of the joint probability in order to determine the expected NPV. So I will simply check some few questions in relation to the decision tree diagram from your past papers. We can check some questions in your past papers. So one of the questions, I want us to start the one for April 2022. We start the one for April 2022. There is a question, number 5, part B, April 2022. There is a question number 5, part B. Question 5, part B. April 2022. There is a question number 5, part B. So that question 5, part B reads that Pop Limited is considering a project requiring an initial investment, requiring an initial cash outlay of 150 million. So the project life is 5 years, after which there will be no expected salvage value. The possible incremental after-tax cash inflows and associated probabilities of occurrence are as follows. So they gave you probability, year 1 net cash flows, conditional probability, then year 2 to year 5 net cash flows. So the company's required rate of return for this investment is 12%. So now required, Roman letter 1, using the decision tree, compute the expected net present value of the project. Roman letter 2, compute the standard deviation of the expected net present value of part B, Roman letter 1. So first, let us draw that decision tree diagram. We shall be required to draw that decision tree diagram before we calculate the expected NPV and also the standard deviation. So to draw the decision tree diagram, so we start off with the initial cost. So initial cost was given in the first paragraph. The amount is 150 million. The amount is meant to be 150 million. So in year 1, there are 2 possibilities. In year 1, there are 2 possibilities. One of the possibilities, there is 0.5 of getting 40 millions. And also 0.5 of also getting 45 millions. So this is meant to be our year 1. This is meant to be year 1. That is meant to be year 1. Then From year 2 to year 5, each one has 3 possibilities. From year 2 to year 5, each one has 3 possibilities. Each one has 3 possibilities. So the first one, they were able to give you 0.2. There is 0.2. There is 0.2 of gaining 40 millions. 40 millions. Also 0.6 of also getting the 15 millions. There is also 0.2 of coming up with 60 millions. Then also this one has 3 possibilities. Even this one has 3 possibilities, whereby they were able to give you a value of 0.1. 0.1 of getting 55 millions. Also 0.7 of getting 60 millions. There is also 0.2 of 65 million. So we summarize it in that order. We simply summarize it in that manner. We should simply summarize it in that level. So remember, this one is year 2 up to year 5. This one is meant to be year 2 up to year 5. That one is from year 2 up to year 5. So once we have done that, we need now to discount those cash flows to get their present value. So cost of capital was given as 12%. So I want us to check in the first table, present value interest factor. What is there as 12% in year 1? To confirm 12% in year 1. In the first table, 12% in year 1 is the same as 0.9. So we get this present value. So get 40 million multiplied by 0. We get the 40 millions. We multiply by 0.8929. So we get this 40 millions multiplied by 0.8929. That's 5.7176.
716.
So that is now for that. Then also I would like us to do the same for this one, whereby we also get 45 millions. We multiply by 0.8929. Discount also this one by multiplying by that. $40.18. So that is now for year 1. It's 40. So we have 40.1. So that is now the present value for the cash flows for year 1. So this one is from year 2 up to year 5. It means it is an annuity. It is the same every year from year 2 up to year 5. So what we do, we shall be using the second table because the cash flows are the same. So present value interest factor for the annuity, 12% in year 5. So the second table is normally cumulative of the first table. The second table is normally cumulative for the first table. So we only want between year 2 and year 5. So we take the one for year 5, we minus the one for year 1. because it is cumulative. So I want you to go to the second table. Check 12% in year 5. So we go to the second table, we check 12% in year 5. 12% in year 5 should be which value? In the second table. 12% in year 5 in the second table. You confirm. Those who are online also check in your tables. You give me the figures. 12% in year 5 in the second table. Anyone who have seen the value? Sorry?
3.6048.
3.6048.
Yes.
Yeah, so we minus the one for year 1. We minus the one for year 1. So the one for year 1 will still be the same as the other one. It is 0.8929. So get the difference to give us now the value. Now get the difference to give us now the value. 2.719. 2.7119. So that will be now our discounting figure, whereby all these figures we multiply by. So we get the present value of that figure. Take 40 million, now you multiply by 2.7119. We now take the 40 millions, we multiply 2.7119. 108.476. Exactly like that. Yes. So we do the same for the second one. The second one, you also take the 50 millions, also multiply 0.8929. You take 50 millions, you also multiply 0.8929. So this one should give us each year. When you take 50 millions, multiply 0, so that's 2.7119. 135.595. We do the same the next one, where you also take the 60 millions, also multiplied by 2.711. 162.714. So that is now for 60 million. So we do the same for the 55 millions. We shall do the same for the 55 millions. 149.1545. So this one you already have it. The one for 60 is 162.714. And finally, we also confirm the one for the 65 millions. And 76.2785. So that is now how to get the present value for those cash flows. So year 1, we just use the first table because it is only one figure. But from year 2 up to year 5, they were annuity, the same every year for that period. So we use the second table. So now from that portion, we want to get the expected NPV. You want to come up with the expected NPV. So to get the expected NPV, we need to create some details about that to calculate the expected NPV, because there are 6 branches. there are 6 branches. So what we shall do, we shall be having the column for the branch. We shall be having the column for the branch. Then we shall also have the column for what we refer to as the present value for the cash inflows, and also present value for the cash outflow. Then you get the NPV, but there is joint probabilities so that you come up with the expected NPV. We can create this schedule, the branch, present value for the cash inflows, present value for the cash outflows, NPV, joint probabilities, and also the expected NPV, joint probabilities, and also the expected NPV. So the question has 6 branches. The question has 6 branches, so we shall be calculating for each branch. The question has 6 branches. We shall be computing for each branch. So we start off with branch 1. We start off with branch 1. So the question has 6 branches. So when it comes to branch 1, remember branch 1 starts from this point, like that. So it ends up at that level. So to get the present value for branch 1, you take this figure of 35.716. Then you add this figure of 108.476. That will be now our branch 1. So branch 1, it is this. So you take 35.716, you add 108.476. That now will give us the present value of the cash inflows for branch 1. Because branch 1 started from this point, like that. So we are looking for the present value. So this one, it is 35.716, which came from the 40. Then you add the one also which came from the 40 as 108.476. So when we add those 2 figures, they should give us around which value? 144, 192. Yeah, so that is now our present value for the cash inflows for branch 1. Then present value for the cash outflow is this figure, the initial cost, which is 150 million. So you subtract 150 million from there. So subtract this from that to give us NPV there. So obviously it will be a negative figure. It will be a negative figure. It is negative what?
5.808.
5.8.
08.
5.08.
No, 5.808.
5.808. Like that. So joint probability multiply 0.5 by 0.2. Joint probability, we multiply 0.5 by 0.2, which is the same as 0.1. Now we multiply this NPV by this joint probability to get the expected NPV. So it will be negative 0.808. Yeah, so that should be now the expected NPV for branch 1. Now we go to branch 2. So branch 2, you will still be using this one because branch 2 will be moving along that, whereby you take 35.716 plus 135.595. So our branch 2, you now add 35.716 plus 135.595. So when you add them together, what should be our present value for the cash inflows? 171.311. Exactly 311.
Yes.
Then This one will not change. The 150 million will not change. So when we minus, it will be 21.311. So joint probability multiply 0.5 by 0.6. Joint probability 0.5 multiplied by 0.6, which will be the same as 0.3. Then now multiply 21.311 by 0.3. 6.3933. That's now our branch 2. We now go to branch 3. We go to branch 3. So branch 3, it is still 35.716 plus 162.714. So you still add 35.716 plus 162.714. So that branch should give us which value? 198.43. So this one still remain 150 million. That one will still remain 150 million. So when we subtract, we get 48 points. Then joint probability 0.5 multiplied by 0.2 is 0.1. So that means it will be 4.8. We go to branch 4. We go to branch 4. Branch 4 now we change to this one. So it is 40.1805 plus 149.1545. So it should be 200 and not. I might still 100. Still 100. 189. So joint probability is still the 150. So it will be 39. So 39.335. So joint probability 0.5 multiplied by 0.1. 0.5 multiplied by 0.1. 0.05. So also multiply 39.335 by 0.05. 1.967. So we go to branch 5. We go to branch 5. So branch 5, you will still add 40.1805. Why are we supposed to run with and it muna add to the zip up. Here round off. Here atakana kuwa 1.967. 1.96675. So it is 1.96675. 1.96675. 56 points. Yes. So we go to branch 5. Branch 5 will still add this value. Then you know 1 and 5. This one comes in. So let us now go to branch 5. Branch 5 will add this one plus this. So it should be 100, 200. 202. Then this one still remains 115. So which means it is 50 what? 52.8945. So joint probability 0.5 multiplied by 0.7. 0.35. So you also multiply to give us the expected end.
18.51 3075.
So 18.513075. So finally, we go to branch 6. Finally, there is branch 6. So branch 6, it is still 40.1805. We add 176.2735. 216.454. So this one will still remain 150. $66.4. Joint probability 0.2 multiplied 0.5. 0.1.
Yes.
So which is the same as 6.1. 6.454. So I would like you now to add this expected NPVs. Get this now total expected NPVs. So now you get those total expected NPVs. Get those total expected NPVs.
Right, 7.8.
Use
That's 7.78.
7.78.
78072.
25. So that is our Roman letter 1, where the question wanted you to come up with the expected net present value. So after we have calculated the expected net present value, we should now compute what is supposed to be the standard deviation, the standard deviation of the expected NPV. So to compute the standard deviation, so standard deviation of the NPV, simply get the summation from the first observation to the last. So N will be 6. There are 6 branches. So we take the NPV of each branch. We subtract expected NPV. So this one, we shall be able to square multiplied by the joint probability like that. Multiplied by the joint probability. So to calculate the standard deviation of the NPV, we shall get the summation from the first branch to the last branch. So the last branch is meant to be 6. So NPV minus expected NPV, you square, multiplied by the joint probability. Then we shall be coming up with the square root for that. We should be coming up with the square root for that portion. We should be able to come up with the square root for that. So these ones are your NPVs. These ones here. These are the NPVs. So expected NPV is this one here, that we have been able to apply. So it will apply to all of them. So your first branch, you take negative 5.808. This was the first NPV. Subtract 37.780725. So that part you square. So joint probability for the first branch was 0.1. So get that figure. We go to the second branch. The second branch is the one of 21. 21.311 million. Your minus still 37.780725 square. Joint probability is 0.3. The next branch is 48.43. We also subtract 37.780725 square. Also 0.1. So we shall add all of them together before we get the square root. So the next one is supposed to be 39.335. You also subtract the same figure 37.780725. So even this one is square 0.05. Also go to the next branch, which is supposed to be 52.8945. Also subtract 37.780725 square multiplied by 0.35. So you will add them together, then you get the square root. You will add them together, then we get the square root for that. So we should add them together, then we also get the square root. So when you get the square root, she will give us around. What is the total when you add? 444.
579.
Right.
Square root is 21.
21,
095.
095,
0125.
0125.
3.
Yes. Online, we are getting which figure? Can we compare and see whether we are getting something closer to that? Online, we compare so that we make the decision. Are we coming across those figures? Someone has confirmed 21.095, which is the same as what we have. Anyone else who have calculated, are you getting those figures? So 21.0950135 is our Roman letter 2. Is our Roman letter 2. So someone else got 21.07. Those are rounding off, but the key issue is 21.0. The key issue there is 21.095. So that should be our standard deviation. Sometimes they normally ask you also to calculate the coefficient of variation. So let us write something brief on the coefficient of variation. Sometimes they may also ask you about coefficient of variation. So let us summarize something brief about the coefficient of variation. But the question only wanted up to the standard deviation. So sometimes they may ask you about the coefficient of variation. So we summarize that coefficient of variation. It is a relative measure of the risk. Coefficient of variation is a relative measure of the risk. A relative measure of the risk. And it indicates the risk per unit of return. It indicates the risk per unit of return. It indicates the risk per unit of return. Then we continue by writing that the lower the coefficient of variation, the lower the coefficient of variation, the less risky the project is. The lower the coefficient of variation, the less risky the project is. The lower the coefficient of variation, the less risky the project is. So if you want to calculate the coefficient of variation, to compute the coefficient of variation, you simply take the standard deviation of the NPV divided by the expected NPV, just in case the question asks. So coefficient of variation, standard deviation for the NPV was 21.0950135. We divide by expected NPV was 37.780725. Just in case the question asks you to compute the coefficient of variation, take the standard deviation of the NPV, divide by the expected NPV, divide by the expected NPV. So that was our first question on the decision tree diagram. That was for the last city. So I also want us to check another question. The other time they tested was September 2021. September 2021. September 2021. There is also a question number 3, part A. September 2021. There is also a question number 3, part A. when you check September 2021, there is also a question number 3, part A. So that question 3, part A for September 2021. Question 3, part A for September 2021, it reads that XYZ Limited is considering buying a new machine, for its manufacturing process at a cost of 10 million. The machine is expected to have a useful life of 2 years with no salvage value. The future net cash flows to be generated in each year are answered. So the estimated cash flows and the probability of their occurrence are given as follows. So they have given you the structure of the decision tree diagram. They gave you the structure of the decision tree diagram. Then additional information, they are saying that not number 1, possibility of abandonment exists after year 1. Then abandonment value is estimated at 8 million. The cost of capital is given as 13%. So now required from letter 1, they wanted you to calculate what should be the expected present value of the project when we ignore abandonment option. Roman letter 2, using suitable computation, justify whether abandonment of the project is viable option. Then Roman letter 3, determine the expected NPV of the project, assuming it is advantageous to abandon the project after 1 year. So that Roman letter 2 should be Roman letter 3. Roman letter 2 should be, so that should be the one for justify. After we have also done expected NPV with the abandonment. Remember, we need NPV without abandonment and also NPV with abandonment before we justify. So that Roman letter 2 should be Roman letter 3. So that Roman letter 3 comes back to Roman letter 2 for us to make the justification, because we need to compare with the abandonment and without the abandonment. But first, we draw the decision tree itself. The first thing you do, you have to draw the decision tree diagram before we want to justify by calculating NPV with the abandonment and also NPV without abandonment. Then we compare the two. So the first thing, we draw the diagram first. We should first of all be required to come up with the decision tree diagram. So in our decision tree diagram, you see they had invested how much in the first paragraph. So our initial investment was 10 million. So year 1 has 3 options. Year 1 has 3 options. There is an option of 0.2 of coming up with the 7 millions like that. There is also 0.4 of coming up with 8 millions. There is also 0.4 of coming up with 6 millions like that. That's now what happens in year 1. So come year 2, each option has 2 possibilities. Come year 2, each option has 2 possibilities. Like now this one, there is 0.6. There is 0.6 of coming up with, that should be 7 millions. 7 millions. Also 0.4 of coming up with 6 millions. Even this one, it has 2 possibilities like that. So there is 0.5 of 7 millions. Also 0.5 of 6 millions like that. Then 0.3, 0.3 of coming up with 8 millions. Also 0.7 of coming up with 7 millions. So that's now our structure of our decision tree diagram. That would be our structure of the decision tree diagram. So after that, we need to discount those figures. So this time it was only 2 years. When you go to the note number 3, the cost of capital was given as 13%. So I want you to check in the first table. What is the present value interest factor? 13% in year 1. I want to confirm what is there as 13% in year 1. 13% in year 1 in the table. 8. So we get 0.8850. So we are discounting these figures. We are discounting these figures. I want you to take 7 millions multiplied by 0.8850. 6.195. That is now for 7 million. We also discount this other one. We also take the 8 millions multiplied by 0.8850. Sorry? 7.08 millions. Then also confirm this one for the 6 millions, whereby you take the 6 millions multiplied by 0.8850. 5.31.
Yes.
Yeah, so that is now for year 1. That is now for year 1, because it had only year 1 and year 2. So we also check for year 2. So this time we are using the first table, because the cash flow is just for 1 period there. So 13% also in year 2. 0.65 and 3. This one here. Not this 5.13. Is it 5.13 or 5.31? 5.31. Okay. So confirm for me this one in the table. 13% in year 2. It is 0.7. 0.7831.
Yes.
Then we start with the 7 millions. We start with the 7 millions. So when you take 7 millions multiplied by 0.7831, it will be able to give us around which figure?
5.4. X17.
So we get 5.4817 billions. You also confirm the next one. The 6 millions also more by 0.7831. Right, 4.6.
986.
Is it 4 or 5?
4.
4.6.
986.
So 7 million, we already have it up there. It was 5.4817. Also, the 6 million you already have. You have said it is 4.6986. Maybe you can now do the one for 8 million. You can do the one for 8 million. So the one for 8 million is which value? 8 not 5, 0.7831.
6.26.
6.2648. The one for 7 million we already had. It was 5.4817. So we have now discounted those cash flows. We have now discounted those cash flows. We need to get the expected NPV. The same approach I have used in the other question. There is the branch. There is the branch. Then present value for the cash inflows. Present value for the cash outflows. NPV, joint probabilities, then expected NPV, like that. So this one had also 6 branches. It also had 6 branches. So we should be able also to come up with a summary for that information. So we start off with, so we shall be able to check what is there for branch 1. What should be there for branch 1? So when it comes to branch 1, it is simply 6.195 plus 5.417. So branch 1 would simply be required to add 6.195 plus 5.4817. So when you add those two figures, it will be able to give us which value? 11.6767. You're given 10 million. You see what is in the initial investment. So when we minus, we get 1.6767. 1.6767. So joint probability, you multiply 0.2 by 0.6. Joint probability, you multiply 0.2 by 0.6, which will give us 0.12. Yeah, so multiply 1.6767 by 0.12.
0.201,204.
So we get 0.201204 minutes. So that's now for branch 1. We also go to branch 2. So branch 2, remember to add 6.195 plus 4.6986. So 10.8936 millions. So we also minus the 10 million, which makes it will be 0.8936 million. So joint probability 0.2 multiplied by 0.4. 0.2 multiplied by 0.4, which is supposed to be 0.1. So multiply that by 0.8936 millions. So 0.71488 minutes. So we go to branch 3. We go to branch 3. So branch 3 you change to, so branch 3 you add 7.08 plus 5.4817. 12.56. We are adding 7.08 plus 5.4817. So this one is still 10 million, which means it is 2.5617 millions. So joint probability, you multiply 0.4 by 0.5. 0.2. So also multiply that 2.5617 by 0.2.
0.51234.
So that is now our branch 3. We go to branch 4. So branch 4, it is still 7.08, but now we add 4.6986. So that one should give you total 11.7786. So this is still 10 million. So which means it is 1.7786. Joint probability 0.4 multiplied by 0.5. It is still 0.2. So multiplied by 1.7786.
0.31572.
So we go to branch 5. We now go to branch 5. So branch 5, you change to 5.31. You have this one plus 6.2648. So it is 5.31 plus 6.2648. 5748. This one is still 10 million. When we subtract, it is 1.5748. So joint probability 0.4 multiplied by 0.3. 0.12. Then now when you multiply 1.5748 is 0.1.
0.188976.
So finally we go to branch 6. Finally we are on branch 6. You add 5.31 plus 5.4817. So that should be able to give us which here 7.7917. 7917. So this one is still 10 million. So that means we have 0.7917. So joint probability 0.4 multiplied by 0.7. So when you multiply by 0.71, 0.7917 should be 0.22.
1676.
So add them together now to give you the expected NPV. So you add them together to give you the expected NPV. So I've seen 1.551404. Yeah, so that is your Roman letter 1. That should be your Roman letter 1. So I said we go to Roman letter 3 before we come back to Roman letter 2. We go to the Roman letter 3 before we come back to the Roman letter 2. But first, I want us to write something about abandonment. So let us write something brief about abandonment. What do we mean by abandonment? So when it comes to abandonment, you simply undertake a project for only a portion of its economic life. Then you sell it. So you don't undertake up the end of the economic life. The reason being, some of these projects, they become more expensive when they get older. So the best way is to have a given period. So the right time to abandon the project is when the expected NPV is maximum. Then it starts declining. So we say that Abandonment means, we write that abandonment means undertaking a project. It means undertaking a project for only, for only a portion of its economic life. Undertaking a project for only a portion of its economic life. A portion of its economic life, and then liquidating the project, and then liquidating the project, and then liquidating the project, and then liquidating the project. Then we continue by writing that the optimal abandonment period, the optimal abandonment period is where the NPV is maximum. The optimal abandonment period is where NPV is maximum, and then it starts declining. The optimal abandonment period is where NPV is maximum, then it starts declining. So we have calculated an expected NPV. This is without abandonment. What we have calculated here is without abandonment. So you have now to check expected NPV with abandonment. So with the abandonment, they are abandoning the project at the end of year one. With the abandonment, they are abandoning the project at the end of year one. So we start by first of all calculating expected cash flows in year one. Expected cash flows. Cash flows in year one. So to get that expected cash flows in year one, you remember this was year one. This was year one. So simply take the 7 million. So this particular 7 million mod by the probability, which is 0.2. We also add, this one is 8 million. Probability of it occurring is 0.4. 0.4. Then we also add, this one is 6 million. Probability of it occurring is 0.4. So we add them together so that we get the expected cash flows in year one. We get expected cash flows in year one. So we simply take those cash flows which were there in year one, but they were subjected to probabilities. We multiply their probabilities, then we add them together. So there are 7 measures. So they were also abandoning it at the end of year one. So we also add abandonment value. So we add abandonment value. Abandonment value. So the question had given you abandonment value in year one. When you check over in the note number 2, you can see note 2. Abandonment value is estimated at how much in note number 2? So it is 8 million. So add there 8 million. So when you add them together, they should give us a total of 15. So we are computing the NPV. NPV is supposed to be given by present value for the cash inflows. We minus the present value for the cash outflows. So we abandon it at the end of year one. So present value for the cash inflows. So present value for the cash inflows, we simply take that 15 million. We discount it at the present value interest factor, 13% in year one. 13% in year one. So this one will be 15 millions. So I want you to remind me what was 13% in year one? What was the 13% in year one? It was 0.8 what?
0.8250.
Yeah, so multiplied by the 15 millions, multiplied by the 15 millions, so that we get the present value of the cash inflows. 13.275. So we less present value for the cash outflows. So present value for the cash outflows was the initial cost of the project, which was 10 millions. So you minus the 10 million. So this is now NPV with the abandonment. So it is 3.275. So that is what was indicated there as the Roman letter 3. That is what was there as the Roman letter 3. So now this is NPV with abandonment. We had already calculated NPV without abandonment. You remember the 1.551404. Yeah, so now you can see when we go back to the Roman letter 3, that is Roman letter 2, where they're saying that using suitable computation, justify whether abandonment of the project is viable. So you can see this NPV with the abandonment is higher than this NPV with the abandonment is higher than NPV without the abandonment. So that means that in that Roman letter 2, we advise them to abandon. So we can have the Roman letter 2 as abandon the project. We advise them to abandon the project because, so abandon the project. So we are advising for the Roman letter 2. Roman letter 2, they had asked you to justify using whether abandonment is viable. So I've said that this is NPV with the abandonment. The other one was NPV without the abandonment. So we can now make a conclusion that abandon the project. Abandon the project because NPV with the abandonment, because NPV with the abandonment is higher than NPV without the abandonment, is higher than NPV without the abandonment. So that's now the justification. So I needed to do one more question on that, but for now I will not be able to finish it. So when we meet in our next class, we shall be doing a question for May 2021. May 2021, question 5, part C. May 2021, question 5, part C. So that we conclude on the decision tree, we do something else. So since you had already another class today, those who are having another class in the morning, we can stop there so that when we meet now, we shall conclude on that. So let us stop there for today.